Hello, and welcome back to A Slice of Physics. We started our discussion on Newton's three laws of motion in the last video with a discussion of the first law, and we now continue with understanding Newton's second law of motion.
If I asked you what the most famous physics equation is, you will surely say E equals mc squared. But if I ask you for the second most famous physics equation, you may think for a little bit and then you will likely say F equals ma. This is simply the equation form of Newton's second law of motion, and you're getting ready to spend some serious time over the next several weeks working with this equation in many different ways. And if you ask scientists, a lot of them will tell you that this is not only the second most famous equation in physics, it's in fact the most important equation in physics, for it helps us understand so much about the natural world that we see around us. So let's take a moment to understand it. Let's start with remembering the equation form of Newton's first law. That simply said that if F is 0, then A is 0. Acceleration is 0 if there is no force. Newton's second law discusses the second half of this equation. What if F is not 0? Well, that's when we get F equals m times A. For starters, you can see that the second law is a superset that includes the first law, because if I have this equation F equals ma, and if I set F as 0,
And m here is mass of the object, which is not 0.
and so the acceleration must be 0. And that was the first law. The first thing this equation tells us is that if there is an external force acting on an object, it changes its state of motion. And the measure of this change of motion is the acceleration, which we know to be the rate of change of velocity. The second thing this equation tells us is that the amount of change of motion, or the amount of acceleration for a given force, depends on the mass of the object. And by the way, I'm putting these little arrows on top of F and A to indicate that they are vectors, while mass is simply a scalar. Let's take a couple of examples to understand this. If I'm standing here and I throw a golf ball, you can imagine how far it'll go before it lands on the ground. Now, if I take the same example, but change the golf ball to a bowling ball and throw it with all my strength, it wouldn't go too far. In both instances, and I'm going to show the golf ball here just so we can see it going farther. In both instances, I applied the same force on the ball. But in one case, the ball went a long distance, and in the other case, the ball went a much shorter distance. Let me write this in equation form. The force I applied in the first case was equal to the mass of the golf ball times the acceleration of the golf ball. And in the second case, the same force was equal to the mass of the bowling ball times the acceleration of the bowling ball. The force in both cases was exactly the same. And so this tells us that the product of the mass and acceleration of each of the balls equals each other. These two things are equal to each other because it was the same force that was applied both times. And you can see that if m times golf ball times a of the golf ball equals m of the bowling ball times a of the bowling ball, and the golf ball has a much lesser mass than the bowling ball, so mg is a lot smaller than mb. For the products to be equal, you can see that the acceleration of the bowling ball must be a lot less than the acceleration of the golf ball. That's why the bowling ball doesn't go far, whereas the golf ball does. Let's take another example. Let's say we have a child who throws a tennis ball across the field and a strong adult who also throws an identical tennis ball across the field. If both of them use all their strength, the child's throw might go that far and the adult's throw might go that far. So in this case, since both the balls are tennis balls, we have two objects of the same mass. So in equation form, we can write this as F child equals mass of the ball times acceleration that's caused by the child, or F adult equals the same mass times the acceleration caused by the adult. And you can see that since FA, force applied by the adult, is a lot more than the force applied by the child, and since M is the same, we're going to get a bigger adult acceleration on the tennis ball than from the child. So we have AA will be a lot bigger than AC. All this is telling us is if I have the same mass, a larger force causes a larger acceleration, which is a consequence of the equation. Whereas in the previous example, we saw that if I have the same force, a larger mass causes a smaller acceleration, also a consequence of the equation. Finally, let me make a comment about the vector form of this equation and what it tells us about the direction of the force and the acceleration. So we have this equation where force, a vector, equals mass, which is a scalar, times acceleration, which is a vector. Moreover, mass is always a positive quantity, it's never negative. And as we discussed before, if you multiply a vector by a positive scalar, the direction does not change. So an important consequence of this Newton's second law, which you will find useful later, is that the direction of the force is the same as the direction of the acceleration. So Newton's second law tells us that when there's an external force applied on a mass, that force changes the motion of the object, resulting in an acceleration, and the direction of that acceleration will be the same as the direction of the applied force. So to summarize, in this video we have discussed Newton's second law of motion, which is represented by this equation F equals ma, and we saw the various things it tells us. First, if I apply the same force on different masses, the larger mass has the smaller acceleration. Second, if I apply different forces on the same mass, the larger force causes a larger acceleration. And third, the direction of the force and the resulting acceleration of the object are always the same.